Good afternoon, students. So in our previous class, we have learned about crystal field splitting of octahedral and tetrahedral complexes. Now we will see how crystal field splitting of d orbitals is happening in square planar complexes. Okay, so in this slide we are seeing that it is splitting in square planar field. Okay, how d orbitals are splitting in square planar complexes. Now here are the d orbitals, 5d orbitals. Okay, and these 5d orbitals are increasing in energy when ligands are approaching. Uniform increase is there. And now when it is forming an octahedral complex, EG orbitals are increasing in energy, whereas T2G orbitals are reducing in energy. Okay. Now EG orbitals are increasing in energy because they are present along the axis, whereas T2G orbitals are reducing in energy because they are present in between the axis. This we have already seen in octahedral complexes. But square planar complex is not an octahedral complex. Okay, square planar complex is just a square. It is in the form of a square. Okay, in octahedral, above and below the square, there are two ligands that are present above and below the square. That's why it is called octahedral complex. Now, in square planar complex, the above and below ligands along z-axis are removed. Okay, so when they are removed, automatically the z orbitals reduce in energy. Okay, so when there are no ligands that are present on the z-axis and it is forming only a square, in case of square planar complexes, the z component, the z orbitals will reduce in energy. So that is what we are able to see here. Here in case of EG orbitals, the z orbitals are reducing in energy, whereas the ligands are present on xy axis. So the dx square minus y square orbitals are increasing in energy. When it is further forming, so here also in case of T2G orbitals also, xz and yz orbitals are reducing in energy, whereas xy orbitals are increasing in energy. And when a square planar complex is perfectly forming, the z component is completely reducing in energy here. Okay, and xy components are completely increasing in energy. Okay, this is x square minus y square present along axis. This is xy present in between axis. So present along axis is completely increasing in energy, and in between axis is increasing in energy, but not to the extent of dx square minus y square. dz square orbital is automatically reducing in energy, and dxz and dyz are further reduced in energy. So this is how the splitting of complex, the splitting of the d orbitals of metal ion occur in case of square planar complexes. In case of square planar complexes, we are able to see here very clearly. Now the difference between delta, the delta splitting of dx square minus y square and dxy, this two splitting difference is nothing but delta square planar. Okay, this is nothing but the splitting difference. Now let us go to the next slide. So here in our next slide, we are able to see the diagrammatical representation of the previous slide. Okay, here first octahedral complex. This is octahedral complex. In an octahedral complex, when so this is x-axis, this is y-axis, this is z-axis, and this is an octahedral complex. This is the central metal ion. This is the central metal ion. And when the ligands that are present on z-axis, when they are removed, so it forms the square planar complex. So this is the square planar complex. Now we are able to see that in case of octahedral complex, EG orbitals are increasing in energy, whereas T2G orbitals are reducing in energy. Okay, EG orbitals are here increased in energy, whereas T2G orbitals are reduced in energy. Now it's very good. Now it's very good. The T2G orbitals are reducing in energy because they are present in between axis, whereas EG orbitals are increasing in energy because they are present along the axis. Now it is now in case of when it is forming square planar complex, the z component orbital ligands are removed. When z component ligands are slowly removed, when they are going far, what happens? The ligands that are present along xy axis, they come near, and the Z orbit ligands will go outside, and the XY ligands will come near and form square planar complex, and the Z component ligands will go outside. So when Z component ligands are going outside, Z orbitals are reducing in energy. Okay, here also the Z component orbitals, XZ and YZ orbitals are reducing in energy. Okay, now the Z orbitals are removed, whereas XY orbitals are increasing in energy because they are present along the XY axis of the ligands. Okay, so dx square minus y square orbitals are increasing in energy, and similarly dxy orbitals or dxy orbitals are increasing in energy. Okay, dxz and dyz are reducing in energy, dx square minus y square are increasing in energy. Now, further when splitting is occurring, dx square minus y square is further increasing in energy, and dz square is further reducing in energy. Here dxy is increased in energy, and dxz and yz, z components are reducing in energy. We are able to see here, z component reduced in energy, z component xz and yz in between axis reduced in energy. Now on the axis reduced in energy, xy in between axis increased in energy, d x square minus y square directly pointing towards the ligands is increasing in energy. Okay, now the difference between dx square minus y square and dx by xy is nothing but crystal field splitting of square planar. This is square planar splitting. This is 0.656 of delta octahedral. This is 0.086 of delta octahedral splitting. Okay, so this is an important slide in which we are able to see from octahedral how it is transitioning to square planar complexes. Okay, octahedral, the Z component ligands are there, whereas when it is forming square planar complex, the Z orbitals are going far apart, and XY orbitals are coming near, and it is forming a beautiful square planar complex in which the Z component orbitals are completely reducing in energy, and the XY component orbitals are completely increasing in energy, and this is a very complex splitting, and that's why this slide is, I have collected this slide from internet in order to explain it properly. Okay, this is a beautiful slide which I got from internet, and it is explaining the how square planar complex splitting is taking place in case of square planar complexes. So in this slide, we are seeing that square planar complex central metal ion is surrounded by 4 ligands. Central metal ion is surrounded by 4 ligands as shown in the figure. Okay, and from the figure it is clear that the lobes of d orbitals point along xy axis, so it will be more affected and suffer larger repulsion. So in square planar complexes, there is a central metal ion, and it is surrounded by 4 ligands on x and y axis. So the ligands that are concerned with x and y axis, or what is happening, the ligands that are concerned with x and y axis, we have already learned that the energy of x and y axis orbitals are increasing in energy, whereas the z component orbitals are reducing in energy. Okay, so in square planar complexes, it is always that the z component orbitals are reducing in energy, and the xy component orbitals are increasing in energy, because z axis there are no ligands, whereas in x and y axis there are ligands that are approaching the metal ion. Okay. Now the second point, from the previous we have learned from the previous figure, it is clear that the lobes of d orbitals point along xy axis, so it will be more affected and suffer larger repulsion. So energy of x square minus y square orbital will be raised most. The lobes of dxy orbital pointing in between x and y axis also gets affected, but to lesser extent than the dx square minus y square orbital. Okay, so that is how it is. From the figure, we are clear that the d orbitals pointing along x and y axis are more affected. There is more repulsion because of the presence of the ligands, and therefore they increase in energy. Whereas the orbitals, d orbitals that are present in between axis, they get much lesser affected, and they reducing energy. These are the z square orbitals, z component orbitals. They reduce in energy, whereas xy component orbitals, they increase in energy. Now here we are the last point shows that square planar splitting is larger than octahedral splitting, and square planar splitting, how much it is larger than octahedral? It is 1.74 times than the octahedral splitting. Okay, very important point. Square planar splitting is larger than octahedral, about 1.74 times, and octahedral is again larger than tetrahedral splitting, which is larger than the pairing energy. So the square planar complexes are usually low spin complexes. So in this slide, we are seeing this is a square planar complex, and ligands are approaching along z-axis. There are no ligands. Ligands are approaching, sorry, along x and y-axis. Okay, this is a square planar complex, and ligands are approaching along x and y-axis. Whereas along z-axis, there are no ligands that are present along z-axis. And this is the splitting that is taking place that we had already studied in square planar complexes, how splitting is taking place in the case of square planar complexes. So this is our next slide, in which we are able to see crystal field splitting of NiCN4 2-. Okay, so this is an example of square planar complex, how square planar complex is splitting. Okay, we are taking NiCN4 2- as an example of a square planar complex and how it is splitting. Now NiCN4 2- is there. NiCN4 2- is a square planar complex. Is a square planar complex. Ni2 plus is the central metal ion. Ni2 plus is the central metal ion. Na2 plus is the central metal ion, and it has a 3d8 electronic configuration. It has a 3d8 electronic configuration. Na2 plus 3d8 electronic configuration is there for Na2 plus, and Ni atomic number is 3d and 4s 4p0. 3d we are able to see that it is 3d8 and 4s2 nickel. 3d8 and 4s2, and Na2 plus 2 electrons are removed from 4s orbitals, and it is having a 3d8 electronic configuration, d8 electronic configuration. And NiCN4 2-, we know that nickel is Na2 plus, and CN4- is a strong field ligand. CN4- is a strong field ligand, and when CN4- is there, it pairs up the electrons that are present, and because it is a strong field ligand, and this is how the electron distribution is happening in NiCN4 2- complex. So these are the d orbitals, and these are d orbitals that are splitting here like this, and this is T2G, this is EG, and this is T2G, and this is EG orbital. T2G is much lesser here, much lesser. EG orbital is above T2G. This is nothing but this is dz and dxz and dyz. This is nothing but dz square. This is nothing but dxy. This is nothing but dx square minus y square. Okay, all x components or xy components are increasing in energy, and z component dz square and dxz and dyz are reducing in energy. Okay, so this is how the splitting is taking place in case of NiCN4 2-, and it is forming a low spin complex. It is forming low spin complex. All square planar complexes are low spin complexes because pairing takes place within the lower energy orbitals, and that's why they are called as low spin complexes. And when we go to the magnetic property, since the complex has no unpaired electron, it is diamagnetic in nature. Okay, the magnetic property, if you are seeing here, since there are no unpaired electrons, it is a diamagnetic. The complex is a square planar complex is diamagnetic in nature. Okay. So till now we had studied in the present class, we had studied how square planar splitting is taking place in case of square planar complexes. How d orbitals are splitting in case of square planar complexes. We have seen the approach of the ligands, then increase in energy of the d orbitals, uniform increasing in energy, and then how they are splitting into T2G and EG orbitals in case of octahedral complex, and how when Z axis ligands are removed, it is forming a square planar complex with Z components reducing in energy and XY components increasing in energy. And we have also seen, we have also studied how NiCN4 2- is a square planar complex, and Ni nickel 2+ is the central metal ion, and how ligands are allowing electrons to pair up, and it is forming a low spin complex. It is forming a low spin complex with no unpaired electrons. Since no unpaired electrons are since there are no unpaired electrons, and it is a diamagnetic complex. Okay, very nice. So in this slide, we are comparing the crystal field splitting of octahedral field, tetrahedral field, and square planar field. Okay, so the first one is nothing but octahedral field. This I have written it on board in order to explain it to all the students. So we are seeing here the comparative crystal field splitting in octahedral, tetrahedral, and square planar complexes. So first one is nothing but A is nothing but octahedral field. So in case of octahedral field, EG orbitals are increasing in energy and T2G orbitals are reducing in energy. So this is the octahedral complex. Ligands are approaching along the XY and Z axis, and the orbitals that are present on the axis will increase in energy. So the orbitals that are present on the axis are nothing but EG orbitals. So dz square and dx square minus y square, whereas the orbitals that are present in between the axis are reducing in energy. They are nothing but dxy, dyz, and dzs orbitals that are reducing in energy. Okay, so now the next one is nothing but tetrahedral field. So this is the diagram which we had already studied. This diagram we had already studied the approach of the ligands along the alternate corners of the cube, and the metal ion is at the center of the cube, and the orbitals that are present along the edges of the cube will reduce in energy, and the orbitals that are present along the center of the cube, okay, which are not influenced by the approach of the ligands along the alternate corners of the cube. So once again, I'll tell properly, the orbitals that are along the axis, okay, center of the faces of the cube, the orbitals that are along the axis, that is center of the faces of the cube, they are reducing in energy because they are not influenced by the approach of the ligands along the alternate corners of the cube. Whereas the orbitals that are present along the edges of the cube, they increase in energy. Because they are present along the edges of the cube, and therefore they increase in energy. And we are able to see here clearly when we compare octahedral and tetrahedral field splitting energy is much lesser when compared to octahedral splitting energy. That is because tetrahedral field, there are only 4 ligands that are approaching the central metal ion, whereas in case of octahedral field, there are 8 ligands that are approaching the central metal ion. So when there are 8 ligands that are approaching the central metal ion, the splitting energy is more. When only 4 ligands are approaching, the splitting energy is much lesser when compared to 8 ligands approaching the central metal ion. And also the ligands that are approaching in case of octahedral are along the axis, and they are directly influencing the orbitals that are along the axis. Whereas in case of tetrahedral complexes, they are approaching the central metal ion along the corners of the cube. So when they are approaching the central metal ion along the corners of the cube, they are influencing the orbitals to a much smaller extent. Okay, that's why the splitting energy in case of tetrahedral field is even much lesser when compared to octahedral field. Now we are able to see here the splitting of a square planar complex. Okay, square planar complex. This is the diagram of square planar complex. X and Y axis is there, and this is the square in which it is forming. Okay, this is the square here of octahedral complex. And when jet component ligands are removed, so this is the square planar complex we are able to see here. This is the square planar complex which we are able to see here. So this square planar complex which you are able to see here, it's a very good perfect complex, square planar complex. And when square planar complex is forming, all jet component orbitals, okay, d yz, d zx are reducing in energy. Okay, these belong to T2G orbitals, and dz square, which belong to EG orbitals, jet component orbital of EG is reducing in energy, whereas the xy component dxy of T2G orbitals are increasing in energy. Similarly, the dx square minus y square of EG orbital is more increasing in energy. So that is how the crystal field splitting of square planar complex is happening. Okay, crystal field splitting of octahedral is quite simple. Okay, octahedral and tetrahedral is quite simple, but the crystal field splitting of square planar is a complex one because there is no jet component ligand. Okay, there is no jet component ligand, and in order to if we want to remember the splitting of square planar complex in a simple manner, we can say that jet component orbitals are reducing in energy and y component orbitals are increasing in energy. Okay, that is how the splitting is taking place in case of octahedral complexes, tetrahedral complexes, and square planar complexes. So this is another slide in which we are seeing this is octahedral complex. This is a octahedral complex. Okay, this octahedral complex, when Z ligands are removed, it is forming a square planar complex. Okay, it is forming a square planar complex. And this is a tetrahedral complex. This is a tetrahedral complex. This is a tetrahedral complex, and a tetrahedral complex, when when the ligands are going towards the xy axis, it is becoming a square planar complex. Okay, this is a just modulation of tetrahedral complex. When tetrahedral complex it is becoming a square planar complex. When jet component ligands are removed from octahedral complex, it is becoming a square planar complex. So here we are seeing that 5 degenerate orbitals, it is splitting into EG is coming down and T2G is going up in case of octahedral complex. Whereas in case of tetrahedral complex, T2G is going down and EG is going up. EG orbitals are going up. And in case of square planar complex, we are able to see here clearly in case of square planar complex. We are able to see here clearly in case of square planar complex, all jet component orbitals are reducing in energy and all xy component orbitals are increasing in energy. Okay. So dx square minus y square is influenced more because the orbitals the dx square minus y square orbitals are along the axis, along the xy axis, that is directly directed on the approach of the ligand. That's why it increases in energy. It increases a lot in energy, whereas xy orbitals reduce in energy, z square orbitals, z component orbital reduce in energy, whereas yz and zx completely decrease in energy because they are present in between yz and zx axis. So that is how octahedral complex splitting is taking place in case of octahedral field, and splitting is taking place in case of tetrahedral field, and how the splitting is taking in place of square planar crystal field. Okay, in our next class, we will study how band structure of solids, how band structure in solids occur. Okay, how molecular orbital by considering molecular orbital as basis, we'll study the band structure of solids in our next class. Okay, so for now we will end our class here.